Welcome to Elementary Algebra, Chapter 17. The chapter is Number Sequences. The author is Harold Jacobs. I'm your presenter, Molly Crocker. This material is copyrighted. Chapter 17, Lesson 3 is about geometric sequences. On to geometric sequences, which can get out to positive or negative infinity quite rapidly or can get closer and closer to zero or to some other number. Did you read the lesson? Let's talk about the amount of wheat that the Persian king owed the inventor of chess. If the story is true, then I'll guess that at some point the supply chief of the Persian king began weighing the wheat being given to the game developer. A web search suggests that a kilogram of wheat, or 2.2 pounds, contains about 33,333 grains of wheat. In the story, the amount of wheat given to the game developer was doubled every day. That's a power of 2. Do you remember how to generate a table of powers of 2 on your calculator? Press the y equals button, then enter 2 raised to the x power. Now, go look at the table. On square 15, the inventor of chess would have received about a kilogram of wheat. The royal supply officer has probably been weighing out wheat for several days now, rather than counting grains, because that's kind of silly. 33,333 grains. Nah. And the game developer is quite happy to do it that way as well, because he doesn't want to check in what he got from the supply officer. It won't matter, but the royal supply officer is beginning to see a problem. Square 16 will be 2 kilograms. Square 17 will be 4 kilograms. Square 18 is 8 kilograms. And for square 19, all the grain required on that day will have to be loaded into a wheelbarrow to haul the grain home. That is only day 20 of 64 squares. This is going to be a problem. Sometime before the king's obligation is fulfilled, the game developer will be a very rich man, buried in a lot of flour. The formula for the nth term of a geometric sequence has some things in common with the formula for an arithmetic sequence. However, instead of a difference that we keep adding on, there is a ratio, and we will continue to multiply by that ratio. For the inventor of chess, taking home grains of wheat, the ratio is 2. Here are the two formulas for the nth term of the kinds of sequences we are considering. The arithmetic sequence is this formula, which we've already studied. And here is the geometric sequence. Notice they both have the expression n minus 1 in them. In the formula for the geometric sequence, the ratio is multiplied again and again. And because we are multiplying a number to itself again and again, we can think of that number as being raised to a power. The ratio is raised to a power. One less power than the corresponding number of the term. For example, the 11th term of the sequence will have been multiplied to the ratio 10 times. We've looked at the sum of the terms formula for the arithmetic sequence. The sum of n terms of a geometric sequence can be found by adding the first term to the second term, which will be the first term multiplied to the ratio. And then we add on the third term, which will be the first term multiplied to the ratio and then multiplied to the ratio again, added to more terms in a similar manner until we get to the next to the last term. That is the term before the nth term, and finally the nth term. The exponent on the nth term will be 1 less than the total number of terms. Now, this next part for developing our formula is a trick, and you have to know the trick. Well, I mean, you won't have to know the trick for the test, but this is a pretty clever trick for developing the formula for the sum of terms for a geometric sequence. Okay, whatever you multiply to one side, you also multiply to the other, correct? I'm going to multiply both sides by r. Stay with me, you'll see where this is going in the next slide. Here is r multiplied to every term. Because I have that ratio showing up more than once in all but the first term, the exponents on r can be combined. And when the r's combined, that exponent is going to increase by 1. So I'm going to simplify this like this. Do you see that? If you need to stop, pause the video here and just examine this for a second, please do so. Now, here's the next step of the trick. From this equation, I'm going to subtract the equation at the top. Both sides of an equation are equal. They're equal to each other. So all I'm doing is subtracting the same thing from both sides, even though it looks different. We did this sort of equation addition and subtraction back in linear systems. Let's cross off the like terms, and I matched them up by color. Notice that the second term of the upper equation matches the third term in the lower equation that's inside the 3 dots. Those are crossed off in green. And the term in the lower row isn't showing here. And the upper row will have a t sub 1 r raised to the power n minus 2, just like that one in the lower row. But it's in the 3 dots there somewhere. Those are crossed off in pink. But that term isn't showing in the upper row. Well, what does this leave us? Now, don't forget we are subtracting, so that negative gets distributed to everything in the lower equation. And on the left of the equal sign, there are 2 terms, r times s sub n, take away an s sub n. And on the right, we have a negative t sub 1 from the second row. We subtracted it, that's why it's negative. And we also have out at the very end t sub 1 r raised to the nth power from the upper row. Do you follow this? Pause here if you need to look more closely. We're not done yet, but I'll continue on the next screen. Okay, we were here with those 2 terms spread way far apart. This was the last line from the bottom of the previous slide. The left-hand side of the equation has an s sub n in 2 terms, and we can factor that out of that side. And the right hand doesn't need the space between the terms anymore. And since t sub 1 is in both of those terms, we're going to factor that out as well. So here's the simplified form of the upper equation. Now, I'm going to reverse the terms of the sum that's in the parentheses on the right-hand side of the equation. So negative 1 plus r raised to the nth power became r raised to the nth power minus 1. Oh, look! We now have s sub n. S sub n is the sum of terms for a geometric sequence. We have it multiplied to r minus 1, so let's divide both sides by r minus 1. And then get rid of the glorified 1. And here is our simplified equation for the sum of terms of a geometric sequence. Whew, that was a lot of alphabet soup. Wait, what's alphabet soup? I keep using that phrase, but it might be an outdated cultural reference. Back when I was a kid, when the dinosaurs roamed the earth and we had to walk uphill to school both directions in the snow with snowshoes on, we could buy soup in cans where the noodles were shaped in the form of letters of the alphabet. Alphabet soup. Now, where would I ever want to use this formula? Oh yeah, what about the inventor of chess? Remember, he walked away with about 1 kilo of wheat from the 15th square, and we now have a formula to say how much he got altogether. Let's plug in what we know. The first term was 1 grain, so t sub 1 equals 1. The ratio between the terms is 2, so r becomes 2. There are 64 squares on a chessboard. That's where the 64 comes from. And do you see how this simplifies? If you don't, toss it onto your calculator. And the number of grains of wheat is this number right here. I'm not even going to try and say it. But how many kilos is that? Well, that many grains divided by 33,333 grains per kilogram works out to be about 5.5 times 10 to the 14th kilos, or 5.5 times 10 to the 11th metric tons. In the wheat growing season of 2024 to 2025, it is estimated that wheat production for the entire world was 793 million metric tons. The amount of wheat owed the game developer works out to be nearly 70,000 times the modern world's production of wheat for a year. If the story has a grain of truth, I wonder what happened to the inventor of chess. Buried in a lot of flour. Time to add these to your notes if you have not done so already. Pause the video here if you need. Let's do an example. Here's a geometric sequence. Let's write the formula for the nth term. We see that the ratio is the square root of 5 because that's what's changed from the first term to give the second term. So plugging this and the first term into the formula, we find the nth term of the sequence is 3 times the square root of 5 raised to the power n minus 1. Now, let's find the sum of the first 5 terms of this sequence. We need the fifth term, so using the formula we just found, let n be 5. You can check on your calculator that the square root of 5 raised to the 4th power is 25. So the fifth term of the sequence is 75. Now let's calculate the sum of the first 5 terms. Here's the formula and the numbers plugged into the formula. The square root of 5 raised to the 5th power lays out like this. It simplifies to 25 root 5. We'll have to continue this on the next slide. We were here, and root 5 raised to the 5th power is 25 root 5. Don't distribute the 3 across the top just yet. Now, do you remember how to clear a radical out of a denominator that contains a sum or a difference? Use a conjugate. Let's foil the radical expressions top and bottom. And let's try and simplify this. What's inside the parentheses has a common factor of 4, so we can factor that out. And that will form a glorified one with a denominator. And finally, we can distribute the 3 across the top, so we get 93 plus 18 root 5. Let's compare this with a list of the first 5 terms, which isn't a very long list. So here's a list of the first 5 terms. Well, it would have been simpler to just add these by collecting like terms, but we landed in the same place. This shows that the formula works. Let's summarize. The formula for the nth term of a geometric sequence is the t sub n equals t sub 1 times r raised to the exponent n minus 1. Now you can read that t sub n as the nth term. So the nth term of the sequence is the first term times the ratio raised to 1 less than the total number of terms. That's another way to say that. Alphabet soup. The formula for the sum of some consecutive terms of a geometric sequence is S sub n, which is the sum of the terms, is equal to a fraction. On the top of the fraction is the first term times the difference of the number of the ratio raised to the number of terms, take away 1, all of that over r minus 1. That's all for now.